This tutorial is to help you understand significant figures. Significant figures are the meaningful numbers in a measurement. So what do I mean by meaningful numbers? What I'm talking about are numbers that actually have meaning in the measurement that you took. For example, let's say that I am measuring the length of this red line, and I look at the ruler and I see that it's around 3.2 centimeters. Now I can say that this line is about 3.2 centimeters. What I can't say is that this line is 3.2185036 centimeters. I don't know that, I didn't measure that, thus those other numbers have no significance. They don't have meaning in this measurement because I didn't measure those. I measured 3.2. So I can't use that as my measurement. I'll have to use the 3.2, which is what I can see in my measurement tool. There are rules for determining how many significant figures you have in a given value. The first rule is that all non-zero digits are significant. So for example, if I have the number 4.3, the 4 is a non-zero digit. The 3 is a non-zero digit. So I know both of those are significant, so 4.3 has two significant figures. In this next example, 871.422, all of those numbers are non-zero. It means there are no zeros in this number. So each one of these digits is significant. If I count those up, I have 6 significant figures. The second rule is that zeros between non-zero numbers are significant. So let me show you an example. If I have 2,108, I have a 0 in the middle of that number. It's between two numbers that are non-zero numbers. It's between a 1 and an 8. So I know that that 0 is significant. It has meaning in my measurement. So I count all 4 of those numbers as significant. So I have 4 significant figures. In this next example, 4,009, now I have 2 zeros in the middle. But they're also between non-zero numbers, so they are also both significant because they're between the 4 and the 9. So all 4 of these digits are also significant. The next rule is that zeros after non-zero numbers with no decimal point are usually not significant. Now the usually part is tricky and I'll explain. So in this number 5,600, there is no decimal point and the zeros are after non-zero numbers. So these two zeros may or may not be significant, but usually we would say they're not. Let me give you a reason why. Let's say that I told you that there are about 5,600 books in a particular library. I'm probably estimating the number of books. I'm not giving you an exact number. So the non-zero digits in that measurement are significant because they're probably correct, but the estimated part, giving it as a rounded off number to 5,600, those zeros are probably not significant. They're probably not exact parts of the measurement. So we would say that the 5 and 6 are significant, giving us 2 significant figures. However, if I went into that library and I counted every single one of those books, and it turned out that yes, indeed, there are 5,600 books exactly, I would put a decimal point at the end to show that I have measured all the way out to the exact number of 5,600. In this case, adding that decimal point in there, that's my way of saying that's how far I measured, and so now those zeros are considered significant. The next rule is that zeros after non-zero digits that are after a decimal point are significant. Here's an example, 5.480. This 0 is after non-zero digits, it's after the 5, 4, and 8, and it's after a decimal point. So I would say that 0 is significant and we have a total of 4 significant figures. Let's look at another example, 7.00. Those two zeros are after a non-zero digit, they're after the 7, and they are after a decimal point. So those are both significant. So in this case, we would have 3 significant figures. The last rule is that zeros before non-zero digits are not significant. Here's an example. 0.039. The two zeros in this example are before non-zero digits. We do not consider these to be significant figures. They are important to the number because they let us know that the first significant figure, the 3, is in the hundredths place by putting those zeros in place. However, they do not give us any significance in the measurement itself. So we say that they are not significant because they don't add to the measurement itself. They are just place values that we need to put in there so that we know where our measurement starts. So those zeros are not significant. The 3 and the 9 are significant because they're non-zero, so we have two significant figures here. Another example, we have two zeros and then 810.00. Now normally we don't write zeros in front of a number like that anyway, but in case you did, or you saw it this way, you know that those two zeros are not significant because they are before non-zero digits. Let's look at the other zeros. The next zero we see is after non-zero digits and before a decimal point. The decimal point lets me know that I did measure all the way out to that spot, so that zero is significant. These two zeros are also after non-zero digits. They're after the 8 and the 1 as well, and they're after a decimal point, so I know they are also significant. So all 5 of those numbers at the end are significant figures. Let's look at some sample problems. Provide the number of sig figs in each of the following numbers. So if we look at A, we have a whole bunch of zeros at the beginning. And remember that zeros before non-zero numbers are not significant. So in this case, only these two 5s are significant figures. So we have 2 significant figures. In B, we have a scientific notation, but we don't actually look at that to figure out how many significant figures we have. So we're only going to look at the first part of this, the 3.40. And in this case, we have a 3 and a 4, which are non-zero, so we know they're significant. And this 0 will also be significant because it's after a decimal point and after non-zero digits. So we have 3 significant figures. In example C, we have 1.6402 grams. So again, we have 1, which is non-zero, 6 is non-zero, 4 is non-zero, and this 0 is between the 4 and the 2, so it is also significant, and the 2 is significant. So we have 5 significant figures. In D, 1.020 liters, the 1 is non-zero, this 0 is between the 1 and the 2, so it's significant. The 2 is non-zero, so it's significant, and the 0 at the end is after non-zero numbers and after a decimal, which lets me know it is also significant. So I have 4 significant figures in example D. In example E, 16,402 grams. I know the 1 is non-zero, the 6 is non-zero, the 4 is non-zero. This 0 is between the 4 and the 2, which means it is significant, and the 2 is significant because it's a non-zero digit, so we have 5 significant figures. And in F, our last example, the 1 is significant because it's non-zero. The 0 is between the 1 and the 2, so it's significant. The 2 is non-zero, but our last 0 is after our non-zero digits, but there is no decimal. So that lets me know that this probably is not a significant 0. So in this case, we only have 3 significant figures. Now we're getting to where we're going to talk about using significant figures when we do mathematical operations. When we add or subtract, the calculated value will have the same number of digits to the right of the decimal as the least precise quantity. So what does this look like in practice? It looks like this. Let's say we add 3.62 and 5.4978. In order to do this, the easiest way is to line them up above each other, above and below each other, so that we can line up the decimal. This is how we used to add when we were in grade school. Rather than grabbing a calculator, we would line these up with the decimals one over the other and then add them. When we do this, we're going to end up with 9.1178. Now, we said that the value that we calculate will have the same number of digits to the right of the decimal as our least precise quantity. So look at our two numbers that we added together. We have 3.62 and 5.4978. See how I've underlined the 2 in 3.62? The fewest number of digits to the right of the decimal. 3.62 goes to the hundredths place, and 5.4978 goes beyond that. So we're going to stop at the hundredths place, which means that we're going to stop in our answer, our calculated value, also in the hundredths place, I should say. So we're going to just draw a line down that says we're separating out the values that we are not going to be able to use. However, we do still have to round this appropriately. So I'm going to look at the number to the right of the digit where I have to stop, which is a 7, and look at the 7 to determine whether I need to round up or round down. And because it is a 5 or above, it's a 7, I need to round up, which means that my answer, instead of being 9.11, will be 9.12. If we multiply or divide, then the number of significant figures in the calculated value will be the same as the fewest number of significant figures in the numbers used in the calculation. That sounds really convoluted, but let's look at what it looks like in an example. So if I take 8.24 times 1.0923, if I put this into the calculator, I get 9.000552. So remember that the number of significant figures in the calculated value, which is my answer of 9.000552, needs to be the same as the fewest number of significant figures in the numbers that I used in the calculation. The numbers I used in the calculation are 8.24 and 1.0923. 8.24 has 3 significant figures and 1.0923 has 5. I have to go with the fewest number of significant figures, which was 3. So my answer can also only have 3 significant figures, 9.00. Again, I'm going to look at the number to the right of that, the 0, and determine whether or not I need to round up or round down. I need to round down, so it stays the same at 9.00. And you might think, but what happens to the 5, 5, and 2? Well, we can't use those because our answer can't be more precise than the least precise measurement that we actually took. It's not like we can make a measurement, do math with it, and then come up with something that's more precise than the actual measurements we took. So our answer is 9.00. Let's do some more examples. Here's some addition. 85.26 grams plus 4.7 grams. Again, remember, with addition or subtraction, line up your numbers so that the decimals are one above the other. When I add these two together, I get 89.86. Remember, I'm going to look at the number that has the fewest numbers after the decimal. And in this case, it's my 4.7. It has one number after the decimal, which means my answer can only have one after the decimal. And so I'm going to draw a line down that separates out the numbers I can't use from the ones that I need to use. I do need to look at the number after to decide if I need to round up or round down, and because I need to round up in this case, instead of being 0.9, if I go up one more tenth from 0.9, I go to 1. So my answer is 90, because 89.9 rounded up to the next tenth would be 90. In a subtraction problem, again, I do the same thing. I line up my decimals, and because 547 does not have a decimal in it, the decimal is understood to be after the 7. It's after the ones place. When I do this subtraction, I get 544.109. I look at the number that has the least number of digits after the decimal, and that is my 547. It doesn't have any numbers after the decimal, so the last digit it has is in the ones place. So my answer also has to end in the ones place. I will look at the number afterward to see if I need to round up or round down. I round down so it stays the same, and my answer is 544. Now let's do multiplication division examples. 31 times 4.892. If I put those in the calculator, I get 151.652. My first value that I multiplied has 2 significant figures, My second one has 4 significant figures. I have to round my answer to the fewest number of significant figures of the numbers that were in my calculation, so I need to round off my number to only 2 significant figures. So I'm going to underline those 2 significant figures, and those are the only ones that I can keep like that, and I need to round my answer off so that I only have 2 significant figures. Now, it's very tempting when we look at the next number, all right, I separate out the ones I'm keeping from the ones that I can't use. I look at the next number to see if I need to round up or down. I need to round down so it stays the same. And it's very tempting to write our answer as 15. However, this is incorrect. That 1 that we have in that place in our answer is a 1 for 100. It's in the hundreds place, so 151.652. So in our answer, that 1 still has to have the value of 100. So we can't use that 1 after my orange line. So we're going to round that off and make it a 0, 150. Remember, if I don't put a decimal at the end of this, then only the 1 and the 5 are significant, and we still have 2 significant figures in our answer. So our answer is 150. In a division example, we have 48.62 divided by 3.50. If I put this in the calculator, I get this very long answer of 13.8914285714. Now remember, our answer can't be more precise than the measurements that we originally took. So I look at the number of significant figures in the 2 numbers I divided. I have 4 significant figures in the first number and 3 in the second number. So I can only go with the fewest number of significant figures, which is 3. So I'm going to underline those, 13.8. And I will separate out what I can't use from what I can, but I do need to look at that next number to decide if I need to round up or round down. In this case, I do need to round up. So instead of 0.8, I will round up to 0.9, and my answer is 13.9. So I've given you a bunch of examples, but if you still have questions, please ask your teacher. I'm very happy to help you.